In our final chapter, what we're going to do is we're going to talk about what's called ANOVA testing. ANOVA testing is going to be a generalization of the t-test. So remember that the t-test is what we used if we wanted to compare different groups of data. So if we had two different things that we wanted to compare, we would use the t-test. And ANOVA is going to allow us to compare three or more groups of data. And so what I want to do is to generalize this t-test. We use this ANOVA test, and we need a new distribution called the F distribution, which we'll talk about in a second. To get into this, I just want to jump right into an example. I think that's the easiest way. This example is oversimplified, it's kind of contrived, but it gets across all the main points in an intuitive way for us to think about ANOVA testing. Intuition, I think, is going to be particularly helpful in this chapter. So what I want to do is, let's say I want to run a study where I want to determine whether or not the foods that a student has for breakfast change how they're going to do on a test later that day. And so what I've done is I've taken 15 students that all have comparable test scores, and what I've done is I've split them up into three groups where I give each group a different breakfast, and then we go through and we give them the test and see how did they do on the test, right? Did the breakfast have any effect or not? And so this is the test that we're going to run. We've randomly assigned each student to a certain group, and there's going to be 5 students in each group. So 5 students that have cereal, 5 students that have eggs, and 5 students that have granola bars. And then we go back and we look at their test scores. And the test scores that we get when we do this study the first time, the test scores that we get are as follows. So for the cereal and fruit group, what we have is test scores that range from 78 to 94. So not centrally organized around a single number, it's kind of spread out, but 78 to 94. For the eggs and toast group, it's 79 to 98, and for the granola bars group, it's 76 to 96. And so the question is, did the breakfast that the student have affect the score that the student achieved on the exam later that day? And the way that we're going to study this is we want to look at how much variation is there in the data among each group. So here, the data vary all roughly similarly. Okay, so they're all going to be more or less equally spread out, and they all basically look the same. So all the groups, more or less, if I were to compare any two of these groups, say the first and last group, they're roughly the same. They're different numbers, but they're roughly the same. They have the same standard deviation, roughly. And so we have to make this decision. Is there more variation among the group or between the groups? And in this case, it looks like there's more variation among each group. And so the effect on breakfast based on the test score is going to be pretty small, because it looks like it's not going to matter too much what the breakfast is. The breakfast really is not going to change too much of what the test score was, because no matter what the breakfast is, the test scores are all basically the same. Okay, so that's the idea. But let's say I run this test a second time, and the second time that we do this, we achieve the following data. Okay, so here, for the second time, if you have cereal and fruit, your test scores are 84 to 89. If you have eggs and toast, you have test scores ranging from 87 to 100, and if you have granola bars, you have test scores ranging from 75 to 79. Here, each of the groups themselves are much less spread out. There's much less variance among each of the groups than there are between the groups. So notice that in any individual group, the spread is very small. Right? We have a small range, we have a small standard deviation and variation, but if we look at the difference between groups, those are huge. So look at the second and third group in particular, right? Those are just different, they don't even overlap. The minimum of 1, so the minimum of the second group is higher than the maximum of the third group. They're just completely non-overlapping data sets. And so now it's much more likely that the choice of cereal does have an effect on the test score, because the variation within groups is much smaller than the variation between groups. So this whole method of what we're going to do is called the analysis of variation. Okay, we want to look at the standard deviation of each of the groups as individual groups, and then we want to look at how do these compare to each other, right? So if we look at the first and second group, do they have different distributions and so on? So this is called an analysis of variance, an analysis of variation test. ANOVA tests use what's called an F distribution, so let's get into that. So an F distribution intuitively just looks at that variation between the groups and divides that by the variation within each group. Now there's going to be degrees of freedom for each of the numerator and denominator. For the numerator, the degrees of freedom is k minus 1, where k is the number of groups. For the denominator, the degrees of freedom is n minus k, where n is the total sample size, so it's the sum of all the sample sizes of the groups, minus the number of groups, so it's n minus k. The F distribution, by the way, is named for statistician Ron Fisher, who either invented or pioneered many of the things that we talked about in this semester. So Ron Fisher is not quite as famous as many mathematicians, but he should be. He really pioneered a lot of this. So the F distribution is named for him. So the F distribution is going to have 2 degrees of freedom, the degrees of freedom for the numerator, the degrees of freedom for the denominator. And the larger the value is, the more likely we're going to reject the null hypothesis. In other words, if we have a very large test statistic, then it's going to be very likely that we say that there's some effect based on which group you're in. Okay, so that's how the F distribution works. And I've graphed the F distribution, by the way, goes from 0 to infinity. So it's not symmetric about the mean. It's kind of like the chi-squared distribution in that sense. In fact, the F distribution is a ratio of chi-squared distributions. So it goes from 0 to infinity. The area under the curve is 1. And it's dependent on 2 degrees of freedom. So what those 2 degrees of freedom are changes the shape overall of the distribution. The F statistic that we're going to work with when we have all these groups of data is going to be as follows. So this F statistic is the quantity that we want to compute. The formula is a little bit more complicated. There's a little bit more math involved, but it's not so bad actually. So the F statistic is given by the following formula. So here, n sub j is the sample size of the jth group. X bar sub j is the mean of the jth group. X bar is the mean of all the data, just grouped all as one. And Sj is the standard deviation of the jth group. Here, n is the total number of data points, so it's all the values n1 to nk added up. And then we're dividing each of these by the degrees of freedom. So there's k minus 1 degrees of freedom in the numerator, n minus k degrees of freedom in the denominator. Okay, so that's the F statistic. Now, what I want to do is, using the F statistic, I want to study example 1. In example 1, what we had was, does the choice of breakfast change the test score in a statistically significant way, say at the 5% significance level? I forgot to add that into the sheet, but let's just say at the 5% significance level. And it turns out when you write down all of these quantities, when you look at the different means, the standard deviations, the sample sizes are all 5, of course, since they're all the same. And when you plug everything in, your test statistic that you're going to get is 0.0106. And if you look at the corresponding p-value, so you can do this with R, your p-value is 0.9895. Okay, so there's an F table that you can use that I'll put on Canvas, so I'll show you how to use that. So in the F table, what you have to do is on the left side and on the top give you the 2 degrees of freedom, and then you can find the critical value that you get there. Okay, so you can use the F distribution to get the critical value, and so just like all the other tests that we can do a critical value approach or a p-value approach. And if you were to look for the critical value approach, what you would find would be that the critical value, we have 2 and 12 degrees of freedom, and we're looking at a 5% significance, so that's a 95% confidence. But the critical value is about 0.3885. Okay, so it's 3.885. 0.01 is far less than that, so we are very safely in the do not reject region. So it looks, at least according to this data, for example 1, that we are not going to reject the null hypothesis. In other words, there is no difference in breakfast, or breakfast has no effect on the test score. So the test scores are not different based on the student's choice of breakfast that morning. All right, what we're going to do next is I want to actually do the same example but with R. So we're going to jump over to R right now. Just newly opened up R, and I want to show you a few commands that are going to be relevant for us. So the first command that I want to show you is the repeat or replicate command. And so what you can do is, let's say I want to have the sequence 1 through 10 repeated 3 times. And so that's what I want my data set X to be. And here we go. So X is 1 through 10 3 times. And that's one way you could do it. You could also have X is 1 through 10. And let's say that what I want to do is I want to repeat. I have to be a little bit careful here. Let's do it this way. Let's say that I want X to be the sequence 1, 4, 5. And I want the first value repeated 5 times, the second value repeated 2 times, and the last value repeated 3 times. So what that's going to do is that's going to give us this value. So this is 1, 5 times, 4, 2 times, and 5, 3 times. Okay, so that's how that value, that's how this function is going to work. And so what I want to do is I want to run the first example that we computed by hand using R. And so what I'm going to do is I'm going to group our data, and I'm going to put, I'm going to let X1, X2, and X3 be these different data sets. Call them whatever you want. Call them A, B, and C. Call them Fred, Mary, and Joe. I don't care. So let's just copy these over. So X3 is going to be those 3 data sets. And what I want to do is I want to construct a data frame that groups these data sets to the different breakfast values that we have. So what I'm going to do is I'm going to define a string here where the first value is cereal, the second one is, say, eggs, and the third one is a granola bar. And so this is just going to be a string. When I put parentheses around the word, this is just going to be a string of characters, meaning just words. So they're not numbers, they're just strings, they're just characters. And what I want to do is I want to construct a data frame. So we talked about how to construct a data frame previously, but what I want to do is I want to construct a data frame consisting of the values x1, x2, and x3. When I put this capital X in front, I could do some of this I could do separately. So I could actually, if I go back, I could just define X as the concatenation of x1, x2, and x3. And then when I list out X, this is all the values. So I could do that. And then what I want to do is I want to look at this data frame of capital X. And then what I want to do is I want to repeat cereal 5 times, eggs 5 times, and granola bar 5 times so that this corresponds to the data. And so the way that I'm going to do that is I'm going to use the wrap function, and let's actually call this, so let's call breakfast. I'm going to repeat the diet string, and I'm going to do this 5 times each. So if I were to look at breakfast, you get cereal 5 times, eggs 5 times, and then granola bars 5 times. And now finally, let's call data df the data frame of X with breakfast. And so what that's going to do is that's going to take our set that we have, and we had our first 5 values that were cereal, our next 5 values that were eggs, so 79, 79, 84, 86, 98. Okay, so those values, and then the next 5 values were granola bar. So this is how we're associating the test score to the different cereal. And that's really the hard part of running an ANOVA test, is kind of constructing this data frame in such a way. But what we're going to do is remember that we called this capital X in breakfast. And so what I'm going to do is I'm going to come up with a formula. And our formula that we're going to do is we're going to compare this AOV is analysis of variance. We're going to compare, it's an analysis of variance model, but we're going to compare capital X to breakfast. And our data is going to be the data frame. Okay, so that's how we're going to define FM1. So if I type in FM1, what it's going to do is it's going to give me a few of the values. It's going to give me the residuals and the degrees of freedom. I'll tell you exactly what that is in a second. Residual standard error is a chapter 15 thing. We totally glossed over that. Don't worry about it. But what I really want to do is I want to run an ANOVA on this formula. So I'm going to take ANOVA times our formula FM1. We got our F value and our P value, which are values that I previously reported to you. And these other values now are easier to explain. So we have the degrees of freedom, so that was 2 and 12. So remember that this was the number of groups minus 1, so 3 minus 1, and the total sample size minus the number of groups, so 15 minus 3. The sum of squares refers to the values in our test statistic. So if I look at this value right here, that's the treatment sum of squares. Okay, so that's the sum of squares that we get here, so 1.2. And if I take 1.2 and divide by the degrees of freedom, I get the treatment mean squares, which is this whole thing. So this whole thing is 0.6. And then same thing here. If I add up these values for the different variables that we have, the different values that we have for these variables, what we get if I add all of those up is the 678.8 number. When I divide it by 12, which is the degrees of freedoms, we get the error mean squares, which is 56.567. And then finally, if I take this 0.6 and divide by 56.57, we end up with this 0.0106 number. That's our F value statistic, and then that spits out the probability. Okay, if I wanted to compute this probability, if I know the F statistic but I don't know the P value, what I can do is I can use so this is just like the P norm and the P T and the P binomial, except here we have an F distribution. So I'm going to do PF, and we're going to look at 0.0106 with 2 and 12 degrees of freedom. And this is going to be the cumulative probability. What we really want to know is 1 minus that. And so that's going to be our p-value, right? 0.989465, whatever, 0.9895. Okay, so that's how we're going to do that. If I wanted to get the critical value, say I wanted to know what F statistic would I need in order for us to go beyond the 5% significance, I could just type in QF 0.95 to 12, and then we would need an F statistic of 3.88 or larger. Our F statistic is way smaller. Clearly, this is not a statistically significant effect based on this data. Okay, so that's how we answer problem number 1. All right, for problem number 2, let's do the same thing. So I'm going to take our data. I'm going to basically run the same test. So we're going to define x1, x2, x3 is going to be our third group of test scores. So we're going to put that in there. Let's call x the concatenation of all of these sets. We've already defined, so I could do this again if I want. I could redefine diet. I could group the diets together. But we've already done that, so I'm not going to worry about it. I do need to redefine the data frame though. So this is going to be x with breakfast. And now I have our new data set that's grouped according to the new test score. So 84 to 89 is test 1. Oops. 84 to 89 is the first group of tests. So those are the ones that had cereal and fruit, right? 84 to 89, and so on. All the others are listed similarly. And so now I'll do the same thing that I did before. I'm going to do an analysis of variance where we compare our data set X to breakfast. Our data set that we're actually using is this data frame, DF, and that's FM1. And then I really want to compute, I want to run this ANOVA test on this formula. And it turns out that our F value is 23.539. Our P value is tiny, so at whatever significance level we want, it doesn't matter if it's at the 5%, 1%, 0.1% significance, this is smaller. This is 7 times 10 to the minus 5, so it's 0.00007. So it's a 7 with 4 zeros before it after the decimal place. So this is smaller. So that means that for this set of data, for the second example, there is a statistically significant effect. Breakfast does affect what test score you're going to get later. Okay, so just again, according to this data. And you have the same thing, the same degrees of freedom. You have different values for the sum of squares and the mean squares and the when you divide each of these by the degrees of freedom. So anyway, so that's how example 2 is going to work. And what I want to do then is let's do a new example. So what we're going to do is we're going to look at 4 different diets and see if there's any change, see if they're all basically the same, or see if there's one that's different than the others. Different doesn't necessarily mean better, but so one of the things to talk about with this ANOVA testing is that ANOVA testing can just tell us that there's a difference in one group between the others. It doesn't tell us necessarily which one is better. Sometimes you can see that just by looking at it, but it doesn't tell you which one is better. So oftentimes an ANOVA is just a first step, right? You have to do this ANOVA testing to see is there any difference, and then later you can do follow-up studies to actually confirm which treatment is better, which diet is better, which medicine is better, whatever. So what I want to do is I want to copy and paste all of these values into R. And what I'm going to do is, let's just call this x1, x2. So copy these values. What these values are is this is the weight loss based on pounds after 4 months of being on a certain diet. So x3 and x4. So let's copy and paste all these values. Oops. And now I'm going to group all the values together. So just like we did before, I'm going to group capital X together, and capital X should have 60 things in it. Each of these sets, x1, x2, x3, x4, all have 15 elements in them. And next what I want to do is let's name the different diets. So I'm just going to list the diets. And so we have the keto diet, the Atkins diet, intermittent fasting. Oops, didn't mean to press enter there. Intermittent fasting and generic calorie restriction. So those are our diets. And then I'm going to repeat this list 15, 12, 17, and 21 times. No, I'm sorry, 15 times each. So 15, 15, 15, and 15. Those numbers come later, sorry. So 15, 15, and 15. And so here, these are the lists repeated. So these values repeated 15 times in the list. And then finally, we're able to construct our data frame, which is going to be our data X compared to this list. And you know what I should do first, actually, is let me define diets as this. I didn't mean to print it. I meant to define it as diets. And then what we're going to do is I'm going to construct our data frame with our data versus the listed diets. And so very nicely what this does is this spits out all the different values that we had in our diets versus which diet it was. So keto, Atkins, intermittent fasting, and generic calorie restriction. All right. And so now we're ready to run the analysis of variance model. And so we're going to compare our data to the diet. Let me make sure I called it diets. Yeah, with an S. I just want to make sure that I use the right term there, otherwise we'll get an error. And the data that we're going to use is our data frame, DF. And that's going to be our formula. And then we want to run an analysis of variance on that formula. And it turns out that our p-value is going to be 0.04, roughly. And so the question, if we go back, was at the 1% significance level, is there a difference in the diets as pertains to weight loss? And the answer is no, because our p-value is larger than 0.01. So in this case, there is no effect. We do not reject the null hypothesis. In other words, all of these diets are the same according to the data at the 1% significance level. A medical research company, and what they want to do is they want to study blood pressure and see what medicines have an effect on a person's systolic blood pressure. So blood pressure is measured using two numbers. There's the higher number, which is the systolic blood pressure. That's the one that we're going to study. The other one is called the diastolic blood pressure. And so what this company wants to do is they want to look at three medicines, which we've creatively called medicine A, B, and C. And they want to know, do these medicines work any better than placebo? And so placebo is this strange effect. If you know what a placebo effect is, you should still look into this a little bit. It's super fascinating. But the idea is that just taking a medicine, even if it does nothing, even if it has no active component, the act of taking the medicine can still have some effect on whatever you're measuring. And actually, it's even stranger than that. There's certain, so for example, there's certain processes that are involved in digestion that can also be affected by placebo, even if you don't know what that process is. So it's not that you need to be aware of the process for the placebo effect to go to work. It's just a totally weird effect. Anyways, so what we want to do is we want to look at these three medicines and compare them to placebo. And so what we've done is we've taken our patient data set and split them up into four groups. So we have the group that gets medicine A, medicine B, medicine C, and then there's a control group. They're not split equally for whatever reason. So there's 15 people that take medicine A, 12 that take medicine B, 17 that take medicine C, and then there's 21 in the control group. The control group is the one that gets the placebo. And so what we want to know is, do any of the medicines work better than placebo? In other words, is there any difference at all between the outcomes of the patients who've taken the medicines versus that of a placebo, right? Because you have to measure it against a placebo in the sense that if the placebo does something, but medicine A, B, and C have the same effect, then they're not really working, right? Because it's just the placebo effect that's being measured there. So this is our problem. We want to know, is there any difference in the effect of any of these medicines versus placebo? And so this is a perfect candidate for an ANOVA test. Here we have four groups that we're looking at, and what we're going to do is I'm going to copy all of this data to R. So this is going to be exactly like the problems that we did before. So I'm going to copy all this data to R. I'm going to define medicine A, medicine B, medicine C, and the control group. Okay, so I'll just call it control group. All right, and so I'm just going to copy and paste the data there. And those are going to be our four sets. I'm going to let X be all of the data put together. Okay, so there should be 65, there we go, 65 values there. And let's see, then I want to list out the medicines. So we're going to have medicine A, medicine B, medicine C, and the placebo. Okay, so that's going to be our list of medicines. And what I want to do is I want to actually define a list of medicines where we're going to take this list and repeat it a certain number of times. And so the number of times that we're going to repeat this is going to be the sample size of each of these groups. So 15, 12, 17, and 21. And you could, if you want, just type in like this, 15, 12, 17, 21. That's a totally fine way to do this. Another way that you can do this, which is a little bit more generalizable, works a little bit better, is you can do the length of A, right? You don't have to compute ahead of time what each of these numbers are. Length of C, and then the length of the control group. Okay, so that's one way to get the meds list. And then we're going to have medicine A listed 15 times, B is 12 times, C is listed 17 times, and so on. Okay. Finally, we're going to construct our data frame. So data.frame. And our data frame is going to consist of our terms X against the medicines. And so this is kind of a cool way to make a table in R. So this has all of the values that we had. So if we just compare this to our list, we had 126, 147, 142, and so on, all for medicine A. For medicine B, we had 161, 139, 133. So 161, 139, 133. So all of the medicines here, we've effectively taken this table from the worksheet and put it in R. And that's really the hard work for all these problems. What we're going to do next is come up with a formula. So we're going to run an analysis of variance model on this formula where we're going to compare our data X to the meds. The data that we're going to actually use is our data frame. And then we're going to run an ANOVA test on that formula. And it turns out that our F value is 12.39. The probability that we have some effect is 1.98 times 10 to the minus 6. That's a small number, so that's a 0 followed by, it's a decimal place followed by 5 zeros. So it's 0.000001982. So that's a really small p-value. That means that if we're just looking at the 5% statistical significance cutoff, then this is going to have an effect. So it turns out that at least one of the medicines is different than the others. I want to point out that in an ANOVA test is not used to tell you which one is better. I mean, maybe in this one you can see that probably it's medicine A. Those numbers on average are lower than the numbers for B, C, and the control group. So it's probably A, but you don't get that information from the ANOVA test. The ANOVA test can only tell you that there's a difference in one of the medicines versus one of the others. So it just tells you that you have two different medicines that have different patterns. Okay, it doesn't tell you which one's better. In order to do that, you have to do certain follow-up studies, and that's beyond the scope of what we're going to talk about in this course. So all we're really worried about for now, all that we want to study, all that you do with this ANOVA test, is you want to know, are there differences in the groups based on the medicine that they're given? And according to our test, the answer is yes, there is a difference. Okay, so that's what we use the ANOVA